All right, I think you can see me now.
Yeah, I can see you now.
All right, thank you for showing up. I was just sitting there wondering if I should record myself talking to myself, basically, or just give everyone the videos from last year. So now I have a reason to actually record it, which is great. So yeah, thank you. Alrighty, so we will get started. Before we begin, I just wanted to ask, is there any questions, or how has the semester been? Hopefully good thus far?
So far, not bad.
Okay,
Easier,
wonderful. Wonderful.
busier.
Good. Hopefully after all the midterms pass, it starts to get a little bit nicer. Yeah.
Hopefully.
Alrighty, so we will begin. Before I do start, I just want to say I really like your name. It's so unique. I love it.
Thank you.
I've never seen too many people with that name, but it's absolutely great. All right, back on topic now. I promise I won't procrastinate too much longer. So assignment 5. Now I'm going to be completely honest, completely transparent. Assignment 5 is a little bit tougher. A little bit. Not a lot, but a little bit. It has 5 questions. The first 3 have to do with stress, and the final 2 have to deal with equilibrium, which is what we covered today. And that video is now uploaded, so you can watch it whenever you like. All right, so I'll just get my clicker working. All right, perfect. So here's question 1. It says that the shown cuboid, and I'll show a picture. It's kind of hard to see. But basically, we have a square under a state of stress shown by the Cauchy stress matrix below. And what happens is on this cube, we're given 3 coordinate points. It says the coordinate points of C, B, and D are given, and that this cuboid is actually composed of 2 halves glued together. So it's a rectangle, but it's actually 2 wedges, and these wedges are glued together kind of right down the seam. Again, I'll show a picture in the next slide. Now it says that the maximum shear stress and the maximum normal stress the glue can take is 100 MPa and 200 MPa respectively. So I like this question because it's almost similar to what we do in actuality. Basically, we have 2 solids, we glue them together, and we're going to apply some stress. And the whole goal of this question is to basically determine, will this break? Will the glue separate? So the question has 3 kind of sub-questions. The first is, what is the normal stress? And the second question is, what is the shear stress? And then finally, after we have our normal stress and our shear stress, all we have to do is compare it to the limits given in the question, and we can say, okay, does it fail in tension, which would have to do with the normal stress, or does it fail in shear? So that's all we're basically doing. Now, if we look at our equations, we're basically analyzing the stress at a point. So if I were to make a cut in my object or my continuum, I have a normal vector which is perpendicular to the cut, and it basically defines that cut. Now, also when I cut, I expose the internal stresses, and we capture those using a traction vector Tn. Now, to calculate Tn, it's just going to be sigma, our Cauchy stress tensor, multiplied by that normal vector n. Now, the traditional formula is technically sigma transpose times n, but in this course, sigma, our Cauchy stress tensor, it's always going to be symmetric. So you technically don't have to transpose it. If you do, great, but it's not really required. All right, so this is going to be the first step. The question itself doesn't want this traction vector, but we're going to need it, because if we want to calculate the normal stress, which is part A, what we're going to do is we're going to take that traction vector and we're going to dot it with the normal vector. So far the equations aren't too bad. If I want the shear stress, tau, it's going to be the norm of our traction vector minus sigma n, our normal stress, multiplied by our normal vector. So as we can see, it's not too bad equation-wise. The only thing we have to ask ourselves is, what are our unknowns? So sigma, we're given right from the question, so that's not bad. The only thing that we're missing is actually going to be that normal vector. That's the only real secret to this question. Once we figure out the normal vector, everything is just plug and chug using these formulas. That's it. So the question becomes, how do we find that normal vector? Well, on the next slide here, this is the picture that we're given. And if we look at what the question gives us, it basically gives us 3 coordinate points. We're given the points of C, B, as well as D. So what we need to do is we need to use these coordinate points to figure out a vector that's going to be normal to that plane A, B, C, and D. So if we look here, we can actually start to visually see that, yes, we have two wedges, and we're basically gluing them together and figuring out, does it fail? The only thing we need to actually calculate to solve this question is going to be that normal vector. So we have to kind of think back to engineering 130 or engineering statics, whatever you want to call it. And we said if we know coordinate points, so in this case B, C, and D, I can actually create position vectors between them. This goes back to Eng 130. So from C to B, I can create the position vector RCB, and then from C to D, I can create the position vector RCD. These are just going to be the coordinate points. And they have nice formulas. The position vector CB is going to be the coordinates of B minus the coordinates of C, and the position vector CD is equal to the coordinates of D minus the coordinates of C. So not too bad. But you may be saying, Clayton, why are we doing this? Why do we care about these two position vectors? Again, the whole goal here is to find the normal vector, which is going to be the vector that is perpendicular to this plane. And if you remember back from our linear algebra part, we said that if we take two vectors and we cross them together, the resultant vector is always going to be perpendicular to the plane. So if we look here, our position vectors, RCB and RCD, they actually define that plane. So if I were to cross them together, I'm going to get a normal vector that's going to be perpendicular to the plane. So that's the real first trick to this question. How do we find what our normal vector is? Well, all we're going to do is cross our two position vectors together. Now there's one other trick, and that is this. When we cross two position vectors together, we are going to obtain a vector that is not necessarily normalized. Chances are, if you guys just put in coordinate points, it's not going to be normalized. Now, a question for you. Does our vector n have to be normalized in order to use those formulas on the previous page? What do you think?
I think so.
Yes. So that's going to be the trick. And that's kind of the major trick when it comes to the stress formulas, is that n needs to be normalized.
Yeah.
So the first step is going to be to find what n is by crossing the two vectors, and then we normalize it. After that, all we need to do is go to the formulas on the previous slide, and we're good to go. It's basically just plug and chug your way towards the answer. So that's question one. Is there any concern with question one, or are we feeling pretty good so far?
So far, so good. Where do we find
So
the position vectors? That's where we get it from the metric sigma.
We get them from the coordinate points. So I didn't
Okay.
specifically, I didn't include it when I wrote out the question.
Okay.
But in your assignments, you'll be given the 3 coordinate points.
Okay, sure.
Perfect. All right, awesome. So we'll move on to question number 2. And as we're going to see, a lot of these stress questions start the same way, where they give us the stress tensor. So in this case, it basically just gives us a stress tensor, and it wants 4 different things. The first one is the hydrostatic stress tensor. The second one is the deviatoric stress tensor. And then it finishes off with the von Mises stress, as well as the principal stress and their directions. So this is going to be the easiest question out of the assignment. It's basically just plug and chug your way to the answers. So the hydrostatic stress tensor, it's simply going to be a diagonal tensor. So as we can see, the diagonal components are P, P, and P, while everything else is 0. And the only real unknown that we have is going to be that hydrostatic stress P. But we have a formula for it, where P is the first invariant of sigma divided by 3. So all I need to do is go sigma 1, 1 plus 2, 2 plus 3, 3, and then divide it by 3. After I find P, I just substitute it into the tensor above, and that's it. That's the hydrostatic stress.
Oh.
Again, it should be nice and simple. The deviatoric stress tensor S, it's also simple once we have our hydrostatic stress. So the deviatoric stress is going to be our Cauchy stress tensor, sigma, minus our hydrostatic stress. That's it. So all we're going to do is we're going to take our matrix sigma, and then we are going to subtract our hydrostatic stress tensor that we calculated in A.
Okay.
That's all we need to do. Happy as can be. We can move on to the von Mises stress. Now, the von Mises stress is kind of funny, where it's easy because it's just plugging in numbers into an equation, but the equation itself, as we can see, it's not so nice. It's pretty ugly when we look at it. But if we were to look at the equation, every component inside we know. We know sigma 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, and 2, 3. So all we need to do is just make sure that we type it into our calculator or Mathematica correctly, and we'll get our von Mises stress. There's no real trick to it. It's just, it just kind of sucks to program, if you will. So that's the von Mises stress. So right away we've done parts A, B, and C. The last thing that it wants is going to be part D, the principal stresses and their direction. So we've kind of seen that principal appears quite frequently throughout this course, because whenever you see the word principal, it's always referring to the eigenvalues. Always, yeah. So whenever you see principal stresses, all we need to do is take our stress tensor and find the eigenvalues. And of course, the directions that they're associated with, well, those are going to be the eigenvectors. So for part D, just need to go eigenvalues, eigenvectors, good to go. In Mathematica, this is very easy. It's just eigenvalues of m or sigma or whatever you define the tensor as. And then the eigenvectors are just going to be the eigenvectors command. After that, it'll basically give you everything you need. Just substitute it into the assignment. Should be a piece of cake. So that's question 2. Are any concerns with question 2, or is it not so bad?
No, so far so good.
Wonderful, wonderful. Hopefully it stays that way.
Yeah.
So question 3. Question 3 is kind of a fun one, where basically we said we have a steel plate, and we are subjecting that plate to the certain applied stress defined by this Cauchy stress tensor. And it says that the uniaxial tension tests indicate that the steel used in the plate yields at 496 MPa. So we're given basically the applied stress in a tensor, and we're given the limits at which it yields. So the whole question here for part A and B is saying, under this applied stress, will our plate yield? So that's what we're going to do. Part A says, will the plate yield using the von Mises criterion? And part B says, will the plate yield using the Tresca yield criterion? So we discussed in the lecture that there's many different ways to try and determine if things have yielded or not. The two specific ones that we talked about, of course, are von Mises and Tresca. In reality, there's many, many, many more. It depends on what you're looking for, basically. Now, the question has some other components where it says in part C, if the plate has not yielded based on the von Mises criterion, calculate a value of T in the following additional stress that, when added to the existing stress, would make the plate yield. So basically, it's kind of a hint that in question A, the plate should yield. If it did, then question C is just useless. So it's kind of a hint that under our stress that we applied, it's not going to yield. And the question is basically saying, what does T have to be that when we add this stress, it will make the plate yield?
Okay.
So we're basically solving for T. Question D is the exact same thing, but we're adding a different type of stress. Now this is very special to us because this stress right here has a very particular form. This right here resembles the hydrostatic stress, if you remember. Remember we had P, P, P,
Yeah.
the rest were zeros? Hydrostatic stress is very special in that it doesn't create any von Mises stress. If I want to, down at the very bottom, that delta sigma, I could have 10 million, 10 million, 10 million. The von Mises stress would actually still be 0. It's a very special case. So if this delta sigma in D doesn't add any stress, will we ever make our plate yield if we add that stress? What do you think?
No.
No,
Yeah.
exactly. So this is kind of a trick question where in part D, it doesn't matter what value of T we have can have infinity. It's still not going to add any von Mises stress, so our plate would actually never yield.
Okay.
And I'll show you what happens in the calculations to show that. But first we'll talk about yield criterion. So the first one is the most simple one, the von Mises. We discussed in the previous question that we have a formula for the von Mises. It's pretty ugly, but we have everything we need. So for part A, all we're going to do is calculate the von Mises stress using our applied stress. And we're just going to compare it to that 496 or whatever the yield stress is. If it's greater than, it's yielding. If it's less than, it's not yielding. So von Mises, usually piece of cake. Tresca has 2 tricks to it. Once you get the 2 tricks, Tresca is always a piece of cake. All we're doing in the Tresca criterion is we're comparing the maximum applied shear stress to the allowable shear stress of the material. So all we're doing is we're using this equation, and we're basically finding the maximum of the difference between the principal stresses divided by 2. So there's 3 scenarios we investigate. Whatever one's the maximum, that's the one we say is our maximum shear stress. The first trick is this. These sigmas are the principal stresses. They're not just the regular sigma 1, 1, 2, 2.
Okay.
These are always the principal stresses. So the first thing we're going to need to do for Tresca is to find those eigenvalues, those principal stresses. After that, we can substitute them in, and we can find what our maximum shear is.
Okay.
The second thing is, if we look on the right-hand side, we're not just comparing to the yield stress. We're actually comparing to the yield stress divided by 2. Because we're not comparing yield stress anymore, we're actually comparing shear stress.
Oh.
So that's why it's divided by 2. If I were to take something uniaxially and just pull it, the maximum shear in that case is sigma y divided by 2. So that's kind of the second trick there. Once you know those 2 tricks, the Tresca is just as easy as the von Mises. Just a little bit more work because of that principal stresses. So far, so
dividing
good.
on both sides, does the 2 need to be applied?
Technically, no. This is kind of the official formula, but you're right. You can just get rid of the 2 on both sides. It'll be the exact same thing. Yeah. So that's the yield criterion. After that, we say, okay, if it doesn't yield in part A, which again it shouldn't, how can we add, or how much T do we have to add so that it does yield? So we have our equation for the von Mises stress, and all those components that we added T to, we can just substitute into our equation, and we know that this must now equal our yield stress. So it's one equation, one unknown. You can use Mathematica, MATLAB. You can solve for what T is.
Okay.
The last trick kind of to this question is when you solve for T, there's going to be 2 values. There's going to be a positive one and a negative one. Because if I want to yield something, let's say I want to yield my clicker, I can either yield it in tension by pulling, or I can yield it in compression. So you're going to get one value of T that's greater than 0 and one that's less than 0. But the question specifically says to use the one that's greater than 0.
Okay.
Yeah, so it's not going to be bad. If we were to look at that other stress state, the hydrostatic one, and we were to substitute that into our von Mises equation, we can see where it starts to cancel. Because in each one of those terms that I'm squaring, we now have a plus T, then minus T. So it cancels out, cancels itself out. So as we can see, the von Mises stress is completely independent of hydrostatic stress. So no matter how much T we add in this case, it'll never yield, basically, is the thing. Yeah. So that's question number 3. Still good to go? Still happy?
Yeah.
Wonderful, wonderful. So we're going to go to question 4. And this has to do with what we learned today in class. So I'm not sure if you watched the video, maybe not, if you're an online student. But that's okay, because there's one trick to this. If you know the trick, everything is easy. Everything is easy. What we talked about today was basically equilibrium. In 3 dimensions, we have 3 equilibrium equations, one for every direction, and we have to make sure it's satisfied, or else it's not physically possible. So if we look at question 4, it says the state of stress inside a continuum is represented by the following matrix. And it says that the continuum that we're interested in has a density of 4 kilograms per meter cubed. That'll make sense once we see the equations. Now in part A, it says, what are the coefficients alpha, beta, gamma, delta, and eta if the state of stress is in static equilibrium when B is equal to 11, 7, and 15. I'll talk about what these mean when we see our equilibrium equations.
Okay.
The second one says, using the coefficients found in A, determine the acceleration vector if B, which is our body forces vector, is equal to 0. So again, it doesn't make too much sense, but basically what we derived today is we have 3 equations of equilibrium. Each equation has basically 3 distinct things. I'm going to bring my mouse on screen. Can you see my mouse?
Yeah, I can.
Perfect. So the first one is it's going to have partial derivatives of our stress components. That's the first kind of thing of equilibrium. The second thing is what we have, or what we call a body forces vector.
Okay.
So this would be something like gravity. If I had gravity on an object, like my clicker, and I drop it, this is what a body force would be. Something that pulls it down, or to the side or something. And then finally, we have basically mass times acceleration. The sum of the forces has to be equal to mass times acceleration. So this is our three equations of equilibrium. We have one for every direction. Rho B, it's typically 0 in the x direction, 0 in the E3 direction, and then of course negative 9.81 for gravity in the y direction.
Okay.
But it could be anything. So as I said in the lecture today, if I'm dealing with something with magnets, there's horizontal attraction between them. That would be a case of our body forces vector. But basically all we need to do is we need to make sure that our Cauchy stress tensor satisfies these equations of equilibrium. And there's going to be one trick, because if we remember in the question, we had we had 5 unknowns, but we only have 3 equations, so there has to be a little bit of a trick. What's nice in part A is it says that we have static equilibrium, which basically means the rho A on all 3 equations is going to be equal to 0. So we're basically just interested in this side over here, and it's equal to 0 in all 3 cases. But again, we seemingly have a problem because we have 3 equations, 5 unknowns. So here's the special trick that I mentioned today in class. If something is in true equilibrium in our continuum, every point inside of our continuum must follow those equilibrium equations. So it's not just 3 equations for the whole body, it's 3 equations for every point inside of the body. So if I had 6 points, that's going to be 6 times 3 equations. That's actually 18 equations. That's the trick here. Every point must be satisfied using these things. So what we're going to do is we are going to create our equations of equilibrium, and then we are going to substitute different points in to try and solve for those variables, if that makes sense. So some good combinations, of course, are going to be when one of the points is 0, because that starts to cancel a lot of things out. Now, when you look at this, it's pretty kind of confusing, I guess, if you will, to see what exactly is happening. So let's go through an example. Let's say we're interested in our second equilibrium equation. So we take our stress tensor, we figure out all the partial derivatives, we know the body forces, and we get this equation.
Okay.
So as we can see right here, we have one equation, but we currently have 2 unknowns. So what we're going to do is we're going to substitute points in to try and solve for these. So again, that has to be valid for any point. You can pick any point you want. So I'm going to pick x1 and x2 over here are both equal to 0.
Okay.
That's a valid point. So my equation, anytime I have an x2, I substitute 0. So this term cancels, this term cancels. I'm left with eta plus 28 is equal to 0. So I can solve for eta.
Yeah.
Then I say, okay, that's great. How about a different point? Let's say x1 is 0 and x2 is equal to 1. Well, now my beta doesn't cancel, so it's in my equation. We still have eta, but now we know what eta is. So now we can solve for this beta term right there. So that's the whole trick to it. It's just picking coordinate points that allow us to solve for those coefficients. After you get that, you're good to go. You can answer part A. Part B is kind of a trolley question. It's kind of silly. So in component form, this is what our equilibrium equations look like in component form. And we said for part A, we had static equilibrium. Basically, everything on the left is equal to 0. Now, part B wants kind of the opposite case. Part B said it's not static, so there's acceleration, but now our body force is equal to 0. This is part B. So if we can see here, part A and B are actually related because this component, all the partial derivatives, those aren't going to change. It's specifically said to use the same coefficients. So the only thing that changed was I took this over here and I just moved it to the other side. So as we're going to see, our acceleration vector in part B, it's actually just equal to the negative of our body forces vector.
Okay.
Yeah, one of those little tricky questions. All right, so that's question 4. How is it? It's
That's
not too
okay.
bad?
Not bad.
Wonderful. So this is when it's going to get a little bit scary.
The bonus
So
question?
brace yourself. Yep. Not a bonus question, unfortunately.
Not yet. Also.
So this is question 5. A lot of text. A lot of text. So I'm not going to read through the text. It's better to show you using the picture. So this is the picture you're given. Basically, we have a beam. It's fixed at the top, and I have a bunch of loads on my beam. I have a point load at the end pulling it down. I have self-weight, so mass times gravity, also pulling it down. And then I have a distributed load pulling it down. And what the question wants is it wants the stress distribution along kind of the length of this beam. That's what it's asking for. So what we basically learned today was equilibrium. And what this question is an application of equilibrium. If we can create a differential equation using equilibrium, we can solve for the stresses. So the whole goal of this question is to create a differential equation and then solve that differential equation. That's it. How do we do this? Well, we talked about in class today that what we are going to do is we are going to take an infinitesimal, so a very tiny slice of this beam. We're going to take a little slice. And on that little slice, we are going to put all of our forces on it so we can analyze how it stays in equilibrium. So the first one that we have, or first thing that we have to do is we have to define the thickness. So I'm going to say that this thickness is dx2. Again, just a very teeny tiny little slice. From there, we can start adding forces to this free body diagram. So the one is we have stress on one side, and on the other side, we have the stress plus the change in stress over the thickness. So of course, depending on how thick this is, the stress is going to change.
Yeah.
So basically, it's going to be equal to the stress before plus that change in stress over the thickness. So that's the first one. That's the major one. The second thing that we have is we have self-weight. So of course, this will act in the center, but I just kind of threw it there to show. So we have self-weight also pulling this down, and then we also have a distributed load. So those are kind of the main forces that we have. Now, the key thing to remember is when we deal with sum of the forces, it's sum of the forces. And if we look here, we don't have forces, we have stresses. So what we need to do is we need to convert all these to their equivalent force by utilizing areas, stuff like that. So we're also going to have to define areas. So on the top here, I'm going to say that this is simply just the area. And on the bottom, this will be the area plus the change in area over this thickness. Same thing that we did for stresses. And now that we have all of this defined, we can actually take equilibrium about it. So what I'm going to do is I'm going to take the summation of forces in that vertical direction. If we look here, this will be our resulting equation. We have basically a stress multiplied by its corresponding area. We have the density times gravity multiplied by its corresponding volume. We have Q times the thickness, dx. And then we have the stress at the top multiplied by its corresponding area. And of course, if this is in static equilibrium, it's all going to equal 0. From there, we can actually do some simplification. The best thing that we can always do in these type of cases to start is just to expand it out, because then we can actually start to see the terms that cancel. Unfortunately, there's only one real term that does, and that is that sigma 22 multiplied by area. On the left-hand side, we have it as positive, and kind of over here, we have it as negative, so they're going to cancel. But as we'll see, another very common thing that'll happen now is every term that hasn't canceled out, it has a dx term, every single one. So what we can do is we can actually factor out that dx term. And since it's equal to 0 on this side, we can actually just get rid of it. If I divide both sides by dx2, well, this goes away. 0 divided by dx2, well, it's just still going to be 0. So now we're left with basically everything in this box right here. And here's the last thing. This is kind of more mathematics, so you don't really need to know why, just know that it happens. If we look in this term, it's special because it's the only term that has a dx2 left in it.
Yeah.
In mathematics, when we integrate curves, you know how we used rectangles originally and then we decrease the rectangle height?
Yeah.
Well, we do the exact same thing here. We have our slice, but if we want the exact solution, we decrease our slice till it's infinitesimal. So basically, with this remaining equation, we take the limit as dx2 approaches 0. So this will get rid of this term completely. And the reason why, again, is we want our slice to be as thin as possible. So in the end, this is what we're left with. This is going to be the differential equation that you need for the assignment.
Okay.
The assignment, it's asking for two things. What is the differential equation, which we have, and then how to solve the differential equation. Now, the assignment, it asks for all the components. So basically, it's going to say, what is the coefficient in front of sigma 2, 2? Well, this would be the coefficient right here, just the derivative of area. It'll say, what is the free terms in the differential equation? Well, that would be these terms over here, because they're independent of sigma. Again, the whole goal is to figure out what exactly this sigma 2, 2 function is. And as we can see, since we have sigma, and we also have a derivative of sigma, it's a partial differential equation. So the final thing in the assignment is saying, okay, you have your differential equation. How do we solve it? Well, let's look at the terms really quick. We know all the constants rho, g, and q. They're given directly in the question. They're not really too scary. The area, we're not specifically given, but we're given all the information we need to calculate that area as a function of x. As we saw, our beam kind of comes down linearly. We can create a function to describe that cross-sectional area as a function of the height of the beam. So that's not a problem. And once we have that function, or the area function, we can take the derivative of it to give us this dA over dx. So at this point, if we actually look, our only unknown is going to be this sigma 2, 2 and the derivative of sigma 2, 2. So all we need to do is solve this differential equation to figure out what exactly that is. Now, what's nice for us is Mathematica has a function specifically for differential equations, and that is going to be this dsolve function. Dsolve function. And what we have to do is basically two steps. The first is we define our differential equation. So let's say that this was my differential equation. I would define it as a times s prime of x. So this is sigma, and we know sigma is a function of x. So I would put s prime of x to show its derivative, plus this term dA over dx. So that can just be the derivative of a with respect to x, times sigma, so times s of x, plus rho g times a plus q, and that's it. I just defined my differential equation. So then once I define my differential equation, I can use the dsolve function by basically giving it three inputs. We give it three inputs, we're good to go. First input, what is our differential equation and what is it equal to? So we have our differential equation defined and we know it's equal to 0. So I just put dE is equal to 0. The second input right here is what is the equation we want to solve for? Well, we want to solve for our stress as a function of x, as a function of the height of the beam. And then finally, the last input is what is the variable inside of that equation? Well, the variable is going to be the height of the beam, x. So that's all we need to do. But there's one last trick. So are you suspicious? Well, probably. And that is this. When we solve differential equations, we have constants. We always have constants. And we would solve for them using boundary conditions. So I'm going to actually just do this, go back to the top, and go back to here. And I'll go from current slide. When we looked at this here, we considered the stress, we considered self-weight, we considered Q, but we left out this concentrated load at the end. This concentrated load, this will be our boundary condition. So basically, if I'm solving for an equation based on stress, I need a boundary condition related to stress. Well, we know at the end of the beam here, so this would be when x is equal to L, the length L, the stress is going to be this P divided by the area at the bottom here. So that's going to be our boundary condition. So the only thing that we have to try and realize then is how exactly do we put that boundary condition into Mathematica? Because we know it exists, but how do we implement it? Well, all we need to do is define what our stress is. So at x equals L, let's say that our stress is just going to be the variable S end. So this is something I would define. I would put it in. When I define our dsol function, all I would do is I'd put parentheses now around this first input, meaning I'm going to input multiple things. I'm still going to have my differential equation is equal to 0, but then I'm going to put comma, the stress at x equals L, well, that is equal to the stress at the end, basically.
Okay.
If I implement it like this, then Mathematica will actually give me my full equation without any unknown constants. That's it.
Okay.
So how was that? Does that sound pretty good?
That's all right. It sounds a lot.
Wonderful. Yeah, no, it's definitely a more beefy one. But I want to start introducing this because, honestly, for the rest of the course, differential equations.
Okay.
So the faster we can solve them now, it'll make our lives a lot easier moving forward.
Okay. Does this reflect how the midterm is gonna be?
No, so what would happen is this next midterm, it stops kind of at constitutive laws, and I wouldn't put a differential equation on that midterm.
Okay.
The final, however, will contain the differential equation of beams. But that differential equation is much easier.
Oh.
It's much more simple. It's nothing crazy like this.
Okay.
It's basically just integrating 4 times.
Okay.
So that's not too bad. Another thing too is in the final, you have complete access to Mathematica.
Okay.
So if you guys want, throw it into Mathematica, you'll be good to go.
Okay.
So I have Mathematica pulled up just to kind of show you how this is done and hopefully maybe answer any questions that you may still have. So which one is Mathematica? This one. Perfect. So you may not know this because it was in the lecture today, but this was in the lecture today. This was our example that we did at the end.
Okay.
We derived our differential equation, and basically we just said we're going to solve it in Mathematica. So I'm going to show you how we did that. It's the exact same differential equation, but there's no self-weight and there is no distributed load. So actually, if I were to go back to PowerPoint and go to the differential equation, it's going to be the exact same as this, but all these terms at the end are gone.
Okay.
So it's like if I were to actually just get rid of those. This is the differential equation we had.
Oh.
Perfect.
So is it always going to be that differential equation, or it changes with the question?
For these specific types of questions, it will actually always be that differential equation.
Okay.
Yeah, it'll always be that differential equation. So another thing too, I guess I'll go back to the PowerPoint. I can't find it. All right, here we go. The scenario it was a horizontal beam. It gave us the function of this length here as a function of x.
Yeah.
That's why I have this right here. So this is the height of the beam as it changes. And then it said that the in-plane thickness was just 1. It's always going to be 1. So the first thing that we do when we solve the differential equation is we want to define what that area is. Well, in this case, it's just going to be base, that in-plane thickness, multiplied by the height of the section.
Okay.
So I'm just going to go base times height. That's it. The other thing that if we look back at the differential equation, the other thing that we need is going to be the derivative of the area. So that's something else I can define really quick. I can say, okay, dA is going to be the derivative of my area function with respect to x. So I'm going to go dA, and it's a function of x. So I'm going to take the derivative with respect to x.
Okay.
So now I have both of these functions defined. Now I can go into actually defining what my differential equation is. So I'm going to go dE, differential equation. You can define it as whatever you want. dE is kind of my own personal thing. It's going to be the stress. So I'm going to say S of x multiplied by the differential of area. So D times A. And then I'm going to add that to the derivative of stress. So S prime at x multiplied by the area, so times A. That's my differential equation. It's exactly the same as we had it here. Stress times the differential of area plus the area times the differential of stress. Now I can go into my dsolve function. So I'll say solution is equal to dsolve. And again, I'm only inputting three things. The first one is, what is my differential equation and what is it equal to? Well, I've defined it as dE, and we know it's equal to 0. The second is, what are we solving for? Well, we want to solve for our stress as a function of x. And then finally, what is the variable inside of that function? Well, we know that's simply just going to be x. So if I were to run this right now, this is what we get. Because notice I didn't put the boundary condition in.
Oh, okay.
So since we didn't put the boundary condition, we have that constant. And that's kind of the trick here. So in order to make that constant go away, we have to define what the boundary condition is. So what I do is I find the stress at the end of the beam, and we know that's going to be that force, that concentrated force P, divided by area, which is kind of the formula for stress. But keep in mind that the area changes over the height of the beam. So we need to specify the area when x is equal to L. So basically the area at the end of the beam. So now this is going to be the stress at the end of the beam. So what I can do is I can now modify my solve function by putting in squiggle brackets. And I can say, all right, my differential equation is equal to 0, but also the stress at L, well, this is going to be equal to this variable, which I found, S end. So now that I've defined that additional equation and I were to solve it, we get, oh, it's because I didn't clear it. SL, well, S end. Did I do the wrong variable? 4 cannot be used as a variable. Huh. Well, this is embarrassing. At x equals L, because I did it in class and it worked fine. But now, of course, I almost wonder if I saved it. So let me just save it really quick. Sometimes when you play with differential equations, it's just MATLAB being dumb. Or Mathematica being dumb. So let me just save it, exit out, and just... Actually, I'm going to exit out completely. And then I'm just reopening it. Sometimes it works. I'm hoping it works.
Yeah, I did that.
Or else we got bigger problems.
I don't know if my program is wrong or...
Yeah, it can be so buggy sometimes. I really hate it. All right. All right. Still says that there is a problem. So S at L.
D is equal to E S L. Is this supposed to be S of X instead of L? No.
It has to be L.
Okay.
Because that is what we are doing. Huh.
Okay.
That is so strange. Well, what I'm probably going to do is figure it out and then edit it into the video.
Oh.
Yeah, because that is, yeah. S end, I've defined it above. Actually, let's see what this is. Oh, that's why. I don't have to edit in. It's not when S equals 4, we have to do this. We have to have an arrow.
Oh, okay.
So it's the dash and then arrow sort of thing.
Okay.
Now if I run it, all right.
How do we do the arrow?
It's, I'll just come down here. It's the dash, so next to 0.
Okay.
And then we do kind of the arrow head. So actually, let me just put it. So it's this, and then it's this.
Oh, okay.
So if we put them together, it'll automatically transform into an arrow. Yes. All right, perfect. So I'll leave it in. Everyone can see my mistake and laugh at me, but that's what it's all about. So when we put in this second equation, as we can see, there's no more constants. We can just throw it all into the assignment and hopefully get some marks. So yeah, that's it for the assignment this week. It's pretty mean because of the last question, but if you have your Mathematica code, it'll go by pretty quick. Perfect. So do you have any questions, or are you feeling pretty good about the
I should
assignment?
be alright, I think.
Perfect. And you have my email, of course.
Okay.
So Any questions at all, always message me. I'm always happy to help.
Sure. For the Mathematica, sometimes when you run a program, it says if it's n, it says n is protected. What does that mean?
Oh, what that means is it's a defined variable. It's like putting in pi.
Oh, okay.
So like if I were to go pi, you see how it turns black?
Okay.
It means it's already defined.
Okay.
So yeah, I think this n is already defined because we use it to get numbers, basically.
Okay.
So if I were to go here and go /n, it puts them in decimal form,
Oh, okay.
sort of thing. Yeah. Yeah, that's a good question. If you're ever defining your own variables, you have to make sure that they are blue.
Oh, okay.
Yeah, if they're black, it means it's already defined. So if I were to go pii, that's good to go. But pi, it turns black, it means it's defined.
Okay. But how comes your L and B are like black? Not that-
It's because I ran the code once. So what happens is the code goes through and it defines them all.
Okay.
Yeah. So it's if you were to do this the very first time, they'll all be blue. But then once you define them once, they'll turn black because you manually define them.
Oh, okay. Okay.
Yeah. Perfect.
I think that's all for today. Thank you so much.
All right, yeah, that's it for today. If you have any questions, again, just let me know. I'm happy to help. If not, have a wonderful weekend. Well, at least it's weekend for me. I know you have school tomorrow, but for me at least.
Have a good one.
All right, thank you. You as well. I'll see you later.